So, hi again.
I guess it's very
Anyway, so I was saying that for let's say what I was saying that I'm starting my talk with I'm starting my talk with the mathematical definition of TQFT given Atiyah, which is a monoidal functor coming from a cobordism category to vector spaces. So of course it comes from Witten's ideas that you want to also object vector spaces and to, let's say, a passage of time between two geometric objects, which is in topology is a cobordism between the two objects. You want to assign a linear operator, and you, as it's encoded by a category, it means that you care about the composition, respecting the composition in some sense. And okay, it has been asked in previous talk, does it exist, this kind of TQFT? Well, it's not totally clear. Namely, sometimes you need to change a little bit to category of cobordisms, adding some inputs, or you need to, sometimes you can change also the target category, enriching vector spaces with much structure, with more structure. And this is the case in the one I will be focusing today. It's a particular case with Kerler-Lyubashenko. And I summarize it up in a theorem saying that if H is, let's call it a BP of algebra, whatever it means, algebra with more structure. If you have such an algebra, you can build a monoidal functor from a category of cobordism denoted like this, cob3 sharp to modules over H. Okay, so here I have changed a little bit the category of cobordism in comparison with what Atiyah did. And also I have enriched vector spaces with more structures. They are modules of algebra H. Let me give an example, of course. We've also seen this in so one example of such functor. So you need to find such an algebra H. And you have a nice example that I will denote F zeta G when H is taken to be the small quantum group at root of unity. Okay, small quantum group. At Q equals zeta, the primitive root of unity. We've seen the definition in Christian's talk. I will explain it later on. So this is the main example. And it works in the case where the category is non-semisimple. So it's one of the first examples where Reshetikhin-Turaev's philosophy applies to non-semisimple categories. And I will work with a slightly different cobordism category as usual, because there in this cob3 sharp, objects are surfaces of this kind. So I choose my favorite model for a surface. Let me read it for you here. Sigma G1R, which means that my surface is of genus G with R punctures and one boundary component. I draw it for here. I drew it for you here. So the boundary component is the rectangle, and you see you have G handles like this, which prove that it's G. And you can also do with mark points like this. I will remove the mark points later on, but just think that what I say can work with mark points. Okay. So these are objects, and a morphism between a surface sigma G and a surface sigma H is a cobordism, which means a three-manifold, and any three-manifold, not a model one, any three-manifold, but I want its boundary to identify homomorphically to this box that I've drawn here. Namely, the box is just the source surface on the bottom, the target surface on the top, and in between, you have still boundary. So you transport the boundary of the surfaces by circle times 0, 1. So the boundary of my three-manifold should identify homomorphically to minus sigma G union S1 times 0, 1 union sigma H, and the junction are made on the rectangle bottom to top. Okay. So excuse me? Okay, if I add some mark points, but I don't want to make complete drawings, you can also add tailors. Okay, but you need to fill in you need to have intervals with ends. Okay. But I'm not discussing manifolds because I would go to simplicity. So you have this composition, okay? You want the composition. And the composition is the stacking of the boxes. Compose M1 with S2, it's composable. You stack those boxes. And you want also a monoidal structure because you want a monoidal functor for some reasons that are very practical for topologies too. And the tensor product here, it's not the disjoint union as in Atiyah definition. For this category, I will take some kind of connected union, connected sum, where I put M1 aside M2 like this. Okay, and this will be my tensor product. Okay. So I have a monoidal category, and it's this one. Actually, I have a little bit more, dealing with Lagrangians, but I want to hide this one. Okay, so let's think that we can create a functor from this cov3 chart to this H matrix. Excuse me? So here it's M1 above M2. So you can stack them only if they are composable, if the target surface of M1 is the source target of M2. Okay. While you can tensor both these things just by putting them aside, and aside you have nothing, right? It's always the same, it's always a rectangle, so you can always. Okay. Okay, I want also to discuss the typical topological byproduct. Okay, why are topologists interested in TQFTs? And you have two famous byproducts. One was widely introduced by Atiyah, is that if you succeed in constructing such thing, what you get is invariance. You can get invariance, numerical invariance of closed tree manifolds. And I'm not going to talk much about them, unless you ask me questions. I will focus on the second famous byproduct of the TQFT, which are linear representation of mapping class groups that I denoted mod sigma. So the mapping class group of the surface sigma. When I put sigma like this, it means any of this kind. Okay. The mapping class group of sigma is the group of homeomorphisms of sigma up to homotopy. Homotopys. So you ask homomorphisms to preserve any choice of orientation, I mean your choice of orientation, and also to be the identity on the boundary. Anyway, that's and you have you take homotopy classes of such homomorphism, and you have a group structure given by composition. Okay, this is what is called the mapping class group. And topologically, how do you get this? Say you have phi homomorphism of sigma. You can assign to it, you learn this in a topological school. You can assign to it I phi, which is called the mapping cylinder. And this mapping cylinder can be seen as an element of my category, namely as a morphism from sigma to sigma, from sigma to itself. So this is included in cov3. Sorry, it's a bit. And how do you build this mapping cylinder? Let me draw it schematically. You take sigma times 0,1. I will do it like this. You take sigma times 0,1, which is sometimes called trivial cobordism, sigma itself. And you take another copy of sigma here, disjoint, and then you glue them. You glue it upon the other one along phi. Okay. So you glue it using glue phi. Okay. You can define it rigorously. I'm not going to do it. I guess this picture is meaningful. And well, you can see this exactly. So to any of these phi, you can assign such an element of my category. Okay. What's remarkable is that it behaves well with composition, this mapping cylinder. Namely, you can compose in mapping class group, you can compose two mapping classes, okay, with the group structure. And this mapping cylinder is equal to the composition of I phi with I psi. But here, the composition is by means of COP3. Okay, I have this composition here. So this is in COP3. This is the composition in COP3. Other remarkable property is that it's invariant under homotopy, because I forgot to say that morphisms are not only any true manifold, is any true manifold with the good boundary up to homeomorphism of it. Okay, and so you take morphism up to homeomorphism. What you get is that if phi is homotopy equivalent psi, then mapping cylinders are equal in COP3. Namely, if you take two homotopic maps, you get two homeomorphic mapping cylinders.
To the boundary, right?
Sorry?
The homomorphism is relative to the boundary.
Yeah. You still you need to write properly. Like a morphism is not only a trimanifold, it's a two-manifold plus the identification here with the boundary, and you have to make everything compatible in a proper way. Okay. At the end of the day, since everything behaves well with composition and homotopy, you get these famous quantum representations of mapping class groups. Namely, you can send, maybe you don't see it right here, but I will.
We can see. We can see. Actually, the up lines, but not really visible. But
okay, well, I won't use them anymore. You create a morphism, group morphism from mod sigma to the automorphism commuting with the H structure, because cobordisms are sent to H module morphisms, or H of the state space associated with sigma. And this morphism is given by the homotopy class of a homeo is sent to the mapping cylinder. Okay? And I will use, okay, I will try to give you a flavor that behaving well with composition of mapping class groups and behaving well with like homotopic things gives the same thing somehow is a very basic property for a homology theory. And we want to use this to rebuild at least these mapping class group representations we get from TQFT. And we expect to be able at the end of the day, one day, to reconstruct the full TQFT. And I will give you a flavor of this. I guess here you go. Okay. Now I will go into my talk. Blah, blah, blah. Yeah, so what I want to say is that the idea, okay, Kerler-Lyubashenko's idea is, resembles a lot like Reshetikhin-Turaev philosophy. Namely, you want first to identify with the true equivalence of category, your category of cobordism with a diagrammatic model. This is precisely what Christian told. Diagrammatic model means not theory. Okay, so not theory plus this surgery axiom. You should add on nots. And once you have this diagrammatic model, you apply Reshetikhin-Turaev philosophy to put a module on each of the strand of your diagram. You get operator and so on. And this is how you get a map from a diagram representing a cobordism onto a morphism of H module. Okay, this is what Christian has done in his talk. And me, I want to rebuild everything, getting rid of this passage. Yeah, I want to avoid diagrammatic model for cobordism. Okay. All right. Let me, okay. I will write a cumbersome theorem right now. And the rest of the talk will be about trying to give you a flavor of what's in the. All right. Let's say that this is the most recent thing we have now. It's in course of writing, but it relies on many things we've done before, besides at each step. And the theorem is the following. Let's see the category where objects with objects equal the set of tuples sigma times an isotopic class of gamma, where gamma is an arc. What does it mean, an arc? It means a simple curve that goes from the boundary. Okay. And morphisms. Hello. All my surfaces, they have one boundary component. So an arc is a simple curve, means it doesn't auto intersect, and you want to go from the boundary to the boundary. Okay. I should put more details here, but I'm not going to enter too much details because it's one set of morphisms. They are embeddings. Let me write it just like this. Namely, if you have an embedding from a surface to another one, it's a morphism. What you should add is that it sends the isotopic class of the arc of the source to the isotopic class of the arc and the arc. This is certainly the thing. You can, for today, you can start by just thinking that my category is just surfaces. Objects are surfaces, and morphisms are embeddings. Maybe you don't have morphisms for the moment, but you can have morphisms as well as embedding a surface into another.
Could I mention zero embedding?
Yeah, it's just
no respect to the boundary.
No, the boundary is not sent to the boundary. It's not sending boundary to boundary. Otherwise, you only have homomorphisms. Here, I relax this, but I still keep track of an arc, which is not the boundary. But this is then what I want to say. It exists a monoidal functor. From C to UQG mod. So the quantum group associated with the algebra sheet. That sends sigma. Maybe I put the rest of the station. So then there exists a monoidal functor. F, Q, G. That goes from C to UQG mod. And that sends a surface sigma. I forget to write the F for the moment. Maybe I say over at the end. It sends a surface sigma to cumbersome object. Sum over n of the H ends of things and sigma relative to part minus the position in the range L sigma. Obviously, I will define all of this later. And an embedding, a morphism that sends sigma 1 in sigma 2 into sigma 2. I send into F push to homology. Okay. So you see, I get rid of any diagrammatic model. It's not a TQFT. Morphisms are just push homology sum.
You said that you are not restricting the boundary, so how do you do with already France?
You okay for the details because you know the story. I just it's not fixing the entire boundary, but it's
The minus.
yeah, exactly. Our base point. Yeah, I'm skipping stuff.
So it's Q.
No, it's not. And by the way, so of course for the moment it's a bit cumbersome. I will discuss this. Conjecture. Once if FQ sigma is evaluated at Q equals theta, it recovers parts of F theta G. No, it's this one. Okay. This is just a conjecture, it's an ongoing reflection, but we have nice ideas. And to still have one theorem based on previous work with the lenses. What happens if you choose one particular object in your category? So let's sigma. And you restrict. How did I write this? FQ restricted to the category, the full subcategory generated by the object sigma and boundary of sigma recovers F and theta etc. Okay, so what does it mean? It means that if you look for the full subcategory generated by this sigma here, and so one fixed object, and you're looking for morphism between this object and itself that preserves the boundary, which means all the mapping classes somehow. So the only morphism you get are the mapping class group, the mapping classes, and this functor recovers Kerler-Lyubashenko's representations of mapping class group of service. Okay. We expect this to work with another G here, quite but well, it's not mapping class group representation is a big part of this category. It's not entire part, so we expect to use this. To do the rest. Okay, so I will follow the following plan. First, I will define for you homologies of configuration space. The second time, I will say a word on how to add action of mod sigma on the homologies. It will be quite natural. Then I will tell you how to add the action of the quantum group. Okay. Because I want this guy to live in modules over utility. And well, in my last part, I will talk about the rest. Maybe I will list like other properties, which ones are already known, which are just objects. Okay. So what does it mean? It means that in the first section, I will explain this thing. Second section, I will explain this. How do you push them out homology? And third section, I will explain this, and I will put code here. I will tell you what do I mean by diffusion model. And I will also explain what do I mean by evaluate at zeta moment. And underline all you don't know with definition. And I might say a word on what do I mean by moment. And, this should be in section 4. Okay. Any questions so far? Otherwise, I'm going into the plan. So I'll start by defining you my main object of study, namely these strange homology stuff. Okay. So 1. Okay. Do you see what I write here? Yes. Good. I will be able to put also stable notation there that remain until the end of the talk. So I want to define some homologies. So homology is a tool defined for any topological space or any manifold. Here I'm going to define manifold associated to a surface, which is the configuration space of this surface. Okay. So if you take N in N, I define proof N sigma, which is the unordered configuration space of N particles in my surface, to be the set of N particles, it's the one to the N, in my surface. I put the braces here to show that they are unordered. It's just a set of particles. And I remove the diagonal. I remove collisions between these particles. Yes. I have another problem is that about the 45-minute constraint. So I will put some black box so that I try to finish on time. And if you have questions, I can tell you on the black box. Okay, so this will be my ground manifold upon which I will be working to reconstruct the TQFTs. And I want to take the homology of this, but I want to take what is called twisted homology. I will say a word on it. And for that, I will assign some black box for today. That is called H of sigma, and it's the Heisenberg. Let's call it the Heisenberg group. Heisenberg group of sigma. For those who know what an Heisenberg group is, as a matrix group, it's one like that. But I should tell you how to assign a particular one to a given surface, namely a surface of type sigma g 1r. So this Heisenberg group should depend on g and r, for instance. And at the end of the talk, maybe I can give more details on what the definition of this group. But for the moment, I will use it as a black box. Okay. Now, also there is the fact. Well, let me write it, and then I will say orally what's hidden. You have the natural morphism from the pi1 of conf n sigma that is surjective onto H of sigma. So somehow H of sigma is a quotient of the fundamental group of. So should I say what fundamental group is? Oh, it's okay. Well, so this again needs a lot of work. Okay. And it relies on earlier work on this group, more precisely, that are called break groups and surfaces. And I'm hidden what's inside because I have hidden what the Heisenberg group is. Otherwise, it will take me 10 minutes. Okay. But think that you have natural group associated to the surface plus the natural morphism from pi1 of n to this here. And in topology, when you have such surjective morphism, this is equivalent to the giving of regular cover. Okay, so you can define a regular cover P n hat that goes from a regular cover denoted conf n hat to conf n. Okay. How do you define this cover out of this morphism? So this morphism is characterized by the kernel, by its kernel. Okay. And this, the kernel is a normal subgroup of this group, and to any normal subgroup of the pi one, you can construct a regular cover associated to it. You can think of this one as conf n tilde, which means the universal cover. As soon as you have a universal cover, you can do this regular cover theory, modulo the kernel of phi n. So on this universal cover, you have an action of the pi one, and you quotient by orbit under the action of the kernel of phi n. And what does the regular cover theory tells you? It tells you that the transformation of the group of this cover, so namely transformation of this cover that doesn't change the evaluation map downstairs, which is usually called the deck transformation group of this cover, is here naturally isomorphic to H of sigma. Okay. Once you have this kind of morphism, surjective morphism from the pi one of another group, you can construct a natural cover, regular cover, upon which the deck transformation group action is given by this Heisenberg. Okay. And out of all of this, I'm defining this thing, which is the nth homology of sigma. So this is a notation. Notation of sigma relative to boundary minus. So I should have said at the beginning that my surface becomes with a marked part, not the boundary, so marked interval in the boundary that I denote delta minus. Okay. So what is this notation? It stands for the nth homology of conf n hat relative to boundary minus underline. I will tell you what it is. Twisted. So sorry, with coefficient in C. Okay. Should I say something about the definition of the homology? I have prepared a crash course, but maybe you can ask at the end. I can say a word on because on what the homology is. Just think that in first approximation, these are abelian groups, a series of abelian groups associated to a manifold, and the number n group of homology somehow deals with n-dimensional submanifold of my ambient manifold. And well, I'm not going to. I'm going to take too much time to.
Mention that the degree is equal to the number of points.
Yeah.
So it is it's a number of detection.
Yeah. So this, for instance, this is a manifold of dimension 2n, right? Configuration space of n points on the surface, and this is precisely the middle dimension. Okay. Good reason to take this, and maybe I say a word on it, but for the moment, let's see what it is. So what is the point? The point is that this is the homology of the cover, but on this you have a natural action of H of sigma. So this is not only an abelian group, you can see it as a module over this, okay? And you can also, in the end, H of sigma boundary minus is a module on what I will call R of sigma, which is just the grouping of H of sigma. Okay. So you have the natural action of the group, but since the homology is defined as linear combination of blah blah blah, you can extend linearly and obtain in the end an action of this ring. Okay. Maybe I say one thing about H sigma. I'm hiding a lot of what this guy is, but it's very important. I will say one thing that should interest you is that the center of H sigma is generated, is an infinite cyclic subgroup generated by an element, and this element I denoted Q. So you have this element Q that commutes with everybody, so you can almost see it as a variable. Okay? As a variable. All right. And yeah, underline. So I can explain to you at the end what homology is, what relative homology is. So you can always take the homology of a manifold relative to a submanifold. And here, the submanifold is the configurations with at least one particle lying on the marked part of my boundary delta. This is again details. And I think I told you all I need. Okay, I told you all I need, and now I can give you, let's start with an example. How can I, so for the moment it's abstract Abelian group, but I can define for you nice elements. Okay, so if I take example, if I take gamma R in sigma and n in integral number, I can draw a diagram. Let's say that this is the boundary of my surface sigma. Okay, and inside somewhere I have this gamma, and I put an index on it, n. Okay, this stands for this diagram. In fact, it's a diagram where I take gamma and I parallelize it n times. So you have n copies of gamma just parallel like this. And this, you can also think of it as an embedding, blah, 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 that I will call maybe gamma n, like this, which is an embedding of I times, so n copies of the interval to conv n. Okay. What does it mean? So I have one interval, two interval, and so on. So I have n interval, and here I have many n intervals inside the configuration space. Since the interval doesn't cross, they are well. This well defines a submanifold of n. And what you can check, I've hidden what homology means, but you can check that it defines the class in Hn of conv n of relative to boundary minus with coefficients in Z. Okay. And next, you should add some little data in your diagram. So to choose a lift of this homology class to the covering space. Okay. This I'm hidden. So I should add something on this diagram. So to indicate the chosen lift plus the choice of lift, it defines a class in H of sigma, Hn of sigma boundary lines. Okay. So I have nice diagrams represented through submanifold of my configuration space, and this submanifold naturally yields a homology class. Homology. So any such diagram like this, of this kind, we define naturally for me a class in this twisted homology. Okay.
So what's the dimension of this homology?
Let me write a theorem. Let me write a proposition. So of course, this homology is infinite dimensional because it's an infinite cover. But you can regard it as a module over this. And then you get finite dimensional assumption. So proposition. Proposition is many statements like this. Proposition is H n of sigma boundary minus is a free pair of sigma module with basis. So free module means that I can choose a generating set of elements with a constant cardinality with basis given by the set. So let me take the surface without functions like this. I will choose obviously usual arcs like this. And I will add indices. This is index A1, index B1, index AG, index BG, in such a way that the sum of the AI plus BI equals N. Okay. What does it mean? Here I use only one curve. Here I have 2G of them. But by means of Cartesian product, this corresponds to a Cartesian product of guys like this. And they still define homology class. Okay? Detail, but somehow here you have n particles lying on this curve. And this diagram corresponds to A1 particles on this curve, B1 particles on this curve, and so on. And so if the sum of the total particles is a good n, what you get is a class in the good homology. Okay? To answer your definition, the dimension of this as a free module over this is the partition of n into 2G numbers, which is 2G plus n minus 1. All right, this is a short presentation of homologies.
Mark points.
For the moment, if I would add mark points, I would have to define for you, well, maybe classes that turns around and add more indices. Okay, I'm just for clarity, I'm going into simplest surface. Okay, so if you're okay with my short presentation of these homologies, still I have less than 10 minutes. I will go quick on the actions of mod sigma, which is in fact quite easy. That's what's nice from this framework, is that now morphisms very easily, the interaction on these homologies very easily, because homology theory is something that is well established now, and it's functorial already. So if F is a homeo of sigma, I assign to it, let's call it abusively F Cartesian product n times, which is an element of homeo of const and sigma. Morally, you just apply F simultaneously to a set of particles. This defines for you a homeo of conf n. Then you have a fact. Okay? It's not always true that you can lift anybody to any regular cover. But because of the property of dysmorphism here you can lift everybody. Okay? So there exists f hat n, which is a homologue from group n to group n hat to group n hat. And also, this is the first fact. Second fact, homology is functorial. Namely, if you have continuous map from a topological space to another, you can push it to homology. It gives you a morphism from the homology of X to the homology of Y. So here, what I get from just the functoriality of homology is that you have a map that I will call Fn hat sharp. That is something that goes from Hn to Hn. Okay, this is just by this homological black box. I can say about it. It's very easy to see how to push the map to homology. That's nice. One problem that could happen is that this is well defined on homology, but this does not keep track of the module structure of errors. Okay? It's not clear that this is a morphism of modules like this. Okay? For the moment, it's just a map of abelian groups. Okay? So actually, it's not true. Not any such map will commute with the R sigma module structure. Okay? But you still have a big subgroup of the mapping class group that is called the Chillingworth subgroup that will act like this. This has introduced in the paper. So in Palmer shown that.
What is the term again?
Chillingworth subgroup. Chillingworth subgroup. It's it deals with preserving some vector fields. And it deals with not preserving such
That's trivially.
yeah, it acts trivially on vectors. But it's still big. It's a little bit smaller than the Tory group for those groups. But it's still a bit. Otherwise, you can also obtain. You can still obtain. I will just write it. I'm skipping a lot of details. But you can still obtain a nice group morphism that goes from mod sigma to haute R sigma, and I will put a hat here. Like this, so you can still have a nice morphism, group morphism from there to there, to the price of extending a little bit the ring R. I will just think that twisted homology is not always functorial. This guy is not always commute with this, but let's in our mind enlarge this ring. We don't know actually, but let's enlarge it and think that we can get this nice morphism. Okay. Let me pause here with one motivation for topologists. These what we usually call abusively sometimes homological representations of class groups. In the case where the surface has no genus, only functions, it has been shown to be faithful by Bigelow. And faithful means injective. And this is how Bigelow proved that great groups are linear groups. You can see them at certain matrices. And we hope to be able to somehow generalize this maybe to higher genus surfaces. Okay, thanks to Bigelow that is giving us a strategy to prove this. So for a topologist, the fact that there exists a proof of injectivity of such kind of thing, relying heavily on homology given by Bigelow, is nice for us, and well, conjecture that might be true for also surfaces of high genus. Okay, this is for the action of mapping class groups, and I will say a word on the action of quantum group. I will also add on this homologies in my third part, and then I will just list briefly how to how to do the rest. So let me give you again the definition of quantum SL2 that Christian gave this morning. This afternoon. We have K such that EKQ commutes with KA, TKE, and F K probably does this. And you have this commutation relation. Me, I like to see it like this. I don't want to give too much detail, but this is quantum SL2. Okay, this famous quantum group arising from the quantized deformation of the enveloping algebra. We can do this with any simple algebra. But this is the SL2 case. So I want to create an operator E, an operator F, and an operator K on my homologies in such a way that these operators satisfy these relations. Okay? Let me define them. In a few words, you can define an operator F that goes from Hn to Hn plus 1. I'm not repeating of sigma relative to waves. And this is more or less, under comma, the Cartesian product with the boundary. So if you have a homology class given by a diagram, you take the same diagram, but you add, you take the same diagram, but you add the interval that goes along the boundary indexed by 1. Increase the dimension by 1 and the number of particles by 1. So you go from Hn to Hn plus 1. For E, you can go to H from Hn. So you have relative homology, gives you nice exact sequence. You have a natural map. Let me hide. That arrives here. H n minus 1. So you can take the boundary map that goes from there to dimension -1 homology of the relative part. What is the relative part? The relative part means you have n particles, but you know that one is fixed on the boundary. You remove it, and you can prove that this is naturally isomorphic to Hn minus 1. So somehow, it's a particle on the boundary, and you remove it. I'm finishing now. K. Oh, yeah. No, I'm not finishing, but anyway. So you add an action of K. And at the end of the action of K is quite simple, it's diagonal on the Hn with a nice coefficient theorem. DNZ with DNZ. This space, the direct sum of all the Hns, is a UQ modulus. Okay. And then, so I told you at the beginning also, by evaluating Q at the root of unity, you recover Lyubashenko's representation. How do you evaluate this? Somehow, there exists, it's a fact also, there exists for all zeta, so primitive, root of unity, blah, 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 plus a choice that I want to hide, rely more or less on the Lagrangian. For this plus a choice, there exists a unique V zeta of sigma, representation of H sigma, that sends Q to zeta times the identity. Okay. This is the standard representations of Heisenberg groups. For given root of unity like this, you have a unique vector spaces with a given dimension. where representation of H of sigma that sends the Q element to zeta times the and where you can, this is, let me call it H of sigma, the direct sum of all of this guy. And you can do H of sigma tensor with V of zeta sigma. I'm hiding some work above R of sigma. You tensor modules of R of sigma. And this recovers Lyubashenko's representations of class loops. And I will conclude without writing anything, just to say, here I told you how to deal with UQSL2. At the beginning, I told you I could call it G. To pass from UQSL2 to any UQG, you have to change the definition of the configuration space. Here, the configuration space, all the particles are unordered. For another Lie algebra, you will take configurations colored by simple roots. So your particles will be colored by simple roots. You can also, it's an ongoing project, you can also relax some collision like this and pass from quantum groups to super quantum groups. Yeah. I would be interested if it has a physical meaning. I've been told that it deals with Rosen-Fermi number. And what do I want to say else? So you can check, okay, you can check the monoidality, because you also have monoidality axioms in homology, called the Kunet formula, excision axioms, and so on. And from these axioms on homology, you get some monoidality, some nice monoidality on your things. And what do I want to say for now? Maybe I'll stop afterwards. You can recover graded blah, blah, blah. You can recover graded version as Christian talked about. And okay, and where should we care about? In my category, I told you there is the objects are surface plus here. Here, I define for you an action of F that adds this particular arc. If your object is a surface plus another arc, you can define another definition of the quantum group where F adds another any. I will stop there. Feel free to ask questions.
We have around 5 minutes for questions and comments.
So, homological is a product, and one considers not just usual model, but then homological models. Structure.
Yeah, sure. This deals with something I've done with Biglow. So today I only talked about UQSL2. I wrote something with Biglow about other quantum groups, and here we focus also on a full Hope algebra structure you want on a quantum. And the reason, so we even recover the quantum group itself as a homology, endowed with a product or product given by topological, the topological thing. You take an empty disk, and this time you take two relative parts, disjoint. The disk is empty, but I take two of this. And then you take all of this, like the direct sum of all the Hn of conf n of this space relative to having a particle parked on one of both. So homology will be generated by this kind of diagram. Okay. And here, so, and you can and on this vector space like this, on this module over on R of sigma, you can define a product, so product, and so on. And the product will be given by stacking, of course. So if I stack the empty disk like this on the empty disk and I forget that I have glued, I obtain a new empty disk. And this will define for us a product. The coproduct will be about, of course, dividing the disk into two. And you can do it very nicely, and it's even easier than stacking. But you still have to say something. add more relative part, then you split the disk into two. But it does the can do it homologically. You can also have an antipode by flipping this 180 degrees. You pass from this figure to the same one. Well, unit for unit and so on, you can write everything. And the result is the quantum group itself, somehow. And then any surface with boundary somehow have, well, as soon as you, well, anyway, and then you can make this algebra act quite naturally. And this recovers the action of UQG I have here.
So just written to keep this in a space, like technically.
Yes. So, I mean, yes and no. The point is that these are not vector spaces. They are modules over some algebra. I can still, so you have Poincare duality in one, and you can still somehow define something that goes from Hn times Hn to R of sigma, which will be linear somehow, blah, blah, blah. And Poincare, if you work with homology, Poincare duality, this kind of pairing are usually a nice intersection computation. So you put your manifold into the line position and you count intersections with signs. And here, there's not only sign because you want to write in, not in Z, but in. So you have this, and this pairing can also be evaluated at infinity. And okay, but it's the result should not be a Hermitian form. So the point of non-semisimple TQFT is that metrics cannot be unitary. Otherwise, entries would be diagonalized by any. You have one very non-semisimple TQFT is the fact that so you have this bilinear form, and once you evaluate this at roots of unity, you know that it will be of mixed signature, not positive definite. This is obliged for non-semisimple TQFT. This is what differs very much from Reshetikhin-Turaev semisimple versions. But yes, still you can recover kind of Hermitian structure of mixed signature from Poincare duality.
Other questions?
So I would like to ask, like, whether it, like, the principles
This one. So at the end you have evaluated Q. So I didn't tell you, but these are operators. I wanted to satisfy this, and you have a Q here. And I told you I have a Q in my Heisenberg group. So to prove that it satisfies this relation, you have to consider the Q in my ring of coefficients. And so once you evaluated Q at this matrix, this is still module on the quantum group at roots of unity. And in the case of Lyubashenko, we proved that we recover what is called the adjoint representation of the small quantum group at roots of unity, which are the state spaces of Kerler-Lyubashenko TQFTs.
And this has like an arbitrary fixed part like this. Like if I take the fixed part for every vector space, fixed part for every system. So
fixed by the action of the quantum group? Yeah. There's work to do. There's work to do. Probably Pierre Godpart has worked precisely so to recover Reshetikhin-Turaev. If you want to caution by fixed, or if you want to do more precisely, if you want to do closed surfaces, if you want to pass from this category to one that is more general with closed surfaces, you will have to caution by some fixed elements and to interpret them very nice. And in the genus zero case, it's in the thesis of Pierre Godpart.
Yes, what he's saying is that it takes a period. The normal is that you have the closed surface, the new module, you can take home from one to this.
Exactly. Yeah, sure. But like Pierre, this is what Pierre did.
But then it's not still semi-simple.
No, it's still non-semi-simple, but he thinks the homology relative. boundary instead of part of the boundary in this way. So I have to. I hope it is not a question. So let us take our speaker. There is more information of the coming talks in our current trimester. So there is already programmed talks for next week, the HRS. Okay, I will let you check the website for all these informations. Otherwise, I would like to thank again our lead speakers, Christian, Giovanni, and Jules.